next talk is by Maximilian Jaroschek, and he'll speak on radicals of Fourier polynomials.
Thank you very much. Yes, as the title says, I'm talking about Fourier radicals or radicals of Fourier polynomials. And usually I don't like it when talks come with a disclaimer, but I think this talk needs one, because it's in a, so this work is in a very early stage. This is due to that when I started this, I was in between two jobs. I finished my job at RISC, and now I'm working at the Max Planck Institute. So it's in a very early stage, and this has both negative and positive consequences for you. The negative consequence is that don't expect any very deep results. So this is very early stage, very early work in progress. So it's nice, but it's not too deep yet. The good thing is that it's very easy to understand. It's a very interesting question from my point of view. And actually you will see a very nice trick later on. Okay, so to motivate what I do a little bit is we look at polynomial factorization. So everybody knows polynomial factorization. In the commutative case, we have given a polynomial with rational numbers as coefficients, and we want to find irreducible P1 to Pm such that P of x equals P1 times P2 and so on. And this has been studied extensively already. One of the more well-known algorithms for this is using Delikamp-Tassenhaus to solve this over a finite field and then lift the results using Van Hoy's algorithm. And usually you don't use this algorithm on the polynomial that you start with, but you do some pre-processing. This is necessary because the input of this algorithm requires a little bit of special form of the polynomial, and also because the complexity is much better if you reduce the degree. So one of the pre-processing steps that you do is you compute the square root decomposition or square root factorization of the polynomial that you have given. So just to remind you what is square free. So we call a polynomial a square free if there is no other polynomial q, such that, which is not a rational number, such that q squared divides p. And a square free decomposition then looks like this. So for every polynomial p, there exists square free and pairwise coprime p1 to pm, such that p is of the form p equals p1 times p2 squared times p3 to the third, and so on. And it's actually rather easy to compute this because of the following observation, that if you take the GCD of the polynomial that you've given and its first derivation, then the multiplicity of the square free factors drops by 1. And this is very nice because this can be turned into an algorithm very easily. So you compute the GCD, and if the GCD is 1, then you already have a square free polynomial, so you just return p. And if not, then you can recursively compute the square free decomposition of G. So this will give you the P2, P3, and so on. And out of this, you can easily compute this P1, and you get P1 to Pm. So this is all very nice. And why am I telling you this? Because now we want to look at the non-commutative case. How does this work for Fourier polynomials? First of all, yeah, this algorithm is nice to see what's happening, but you don't actually compute it like this. You would use a better algorithm, it's called Yun's algorithm, because this algorithm here, the complexity depends on the number of square free parts that you have. And in Yun's algorithm, the complexity is independent of that. Okay, so what are Fourier polynomials? Fourier polynomials are polynomials for which the multiplication is not commutative. And what this does, it takes your very nice and happy ring of commutative polynomials and turns it into a ring of grief and despair where nothing works. So, especially for factoring Fourier polynomials, it's horrible because the factorization is not unique in some sense, which can be well defined. But even though it's not unique and even though it's a very hard problem to solve, there are some algorithms who achieve what we want to do. For example, Kiesbeck and Zhang, they have an algorithm which works over finite fields, and in a collection of papers of Bornstein and Petkovsek, they give classical algorithms on this, how they were solved for certain Fourier algebras. And just recently, we also talked by Albert, which was given here, with Mark Kiesbeck, Albert Heinle, and Victor Lewandowski. They have a nice algorithm for factoring Fourier polynomials in the multivariate case. But the thing is, there is no square free decomposition. So they don't have any pre-processing going on. They have to take the Fourier polynomial as it is and work with it. And why is this? Because in the non-commutative case, we don't have a derivation of operators. So how I came up with this problem actually is when I visited Mark Giesbrecht in Waterloo, and Albert was telling me that they have a formally defined derivation which satisfies some properties. And my first question was, does this work to get a square decomposition? And the answer was no, it does not work, which was a pity. So and it is interested me in the following problem. So we want to define something which I call right square freeness. So I want to find the square free decomposition of an Euler polynomial. What is unlikely is that if you have given an Euler polynomial which is equal to P1 to the K1, P2 to the K2, and so on, that we will somehow get P1 times P2 times P3 and so on. Why is this unlikely? Well, because accessing these factors which are in the middle is rather difficult. If you've worked with Euler polynomials before, you know that you can access somehow the factors that are on the right and the factors that are on the left, but factors in the middle are very difficult to get hold of. So my goal would be that if I have given an operator P, which could be written in the form A times L to the K, I want to be able to compute P tilde, which is equal to A times L. So I want to remove this K here. And this would be my ultimate goal. This I did not achieve yet. But what we will care about in this story will be the easier problem if the A equal to 1. That is, if we have given P equal to L to the K, we want to compute L. So, and there you have to realize that these two problems are kind of different because consider which K we are looking for. So if P is in the form of A times L to the K, for example, it could be like something like this, then the decay that you're actually looking for would be this 2 here, so the smallest K that you can find, because then you would apply the algorithm recursively on this part. And for this problem here, you want to find the largest K. So in this case, it would be 10, because if you only find 2, then you would end up with L to the 5, and you want to find L and not L to the 5. Okay, so the question in this talk is, given an Euler polynomial P, find an Euler polynomial L and a natural number K such that P equals L to the K and K is maximal. And how will we achieve this? So this is the outline of the algorithm in total and the outline of the rest of my talk. So first we will check for degenerate cases, then we will compute candidates for K, and then we will find L by linear system solving. This second part here will be more or less optional, but it's nice to do through reducing the complexity of the whole algorithm. Okay, and for doing all this stuff, now we have to get a little bit more into detail, so I will define what Euler polynomials are. So we let sigma be an injective endomorphism, so that goes from the rational functions to the rational functions, and delta be a so-called pseudo-derivation, which is such that it's linear. So sigma of A plus B, delta of A plus B will be equal to delta A plus delta B, and it satisfies this skew Leibniz rule. So if you're not familiar with this, don't worry, you don't have to remember this, you just have to remember that there exists some delta like this. Okay, and the ring of Euler polynomials are then is the set of polynomials with rational coefficients, with component-wise addition and the following multiplication rule. You multiply them as usual with commutative polynomials. Just if you get into the case where you have the indeterminate y times a rational function, then this does not commute. So y times a is not equal to a times y, but it is equal to sigma a times y plus delta a. And this ring we denote by this here. And two prime examples for this are the shift operators. So we take the rational functions over Q, and the multiplication works as a shift. You will see an example on the next slide. Or the derivation case, so where this will be the differential operators. For this talk, I will focus on this example here, just because I prefer it. I like it more to work with this. Okay, a small example for how the multiplication works. If you take, for example, L as this operator, then if you multiply L times L, you see in the leading coefficient of the product, you get not x squared, but x times x plus 1, because here when you multiply s by x, you get the shift. in there. Okay, but this L is not too interesting. Later on we will work with this L, but don't worry, you also won't have to remember this. Just I wanted to show with which example I will work on the next few slides. Okay, then so in the outline of the algorithm, I thought first we check for degenerate cases. What are the degenerate cases? Of course, obviously, if the degree of my Euler polynomial in the non-commutative variable s is equal to 0, then I have just a commutative polynomial, and I can do it like in the commutative case. But there's another degenerate case, and this is when the degree in x of my Euler polynomial is 0. So then the coefficients of the Euler polynomial will be just rational numbers, and this is called the C-finite case. And also there the multiplication works as in the commutative case. So in these two cases, I can just do it as I would normally do. And how's that? So what I do is take the square free decomposition of a commutative polynomial, so for example like this. And if p is equal to L to the k for some L, then and k is a natural number, then for all the indices I have here in my square free decomposition, it has to hold that pi is not equal to 1 if k divides I. And then k divides I. So what I can do is to get L out of p is I compute the square free decomposition, p1 to pm of p, and I compute the GCD of all the indices in a square free decomposition, where pi is not equal to 1, of course. And then I return this polynomial here, where it just divides the exponents by k. This is rather easy. So now, for the Euler polynomial, for the non-degenerate case, now we have what we can do is we can compute some candidates for k. How is this? So we let p be this Euler polynomial here, and L be this Euler polynomial here, where p is L to the k for some k. And obviously, k has to divide the degree of p in s, and the degree of p in x, and the degree of the leading coefficient of p, and the degree of the trailing coefficient of p. But also, when you look at this equation here, and you write it out, so p is equal to L to the k, if you write it out, then p is equal to L times L times L, and so on. And we continue this, and then we look at the constant coefficient. There we see that p is equal to L0, so that the constant coefficient of L to the k. And this is what we had in the commutative case. So k is among all the common divisors of what I have given above here. So the degree of s, degree of p and s, in x, the leading coefficient and constant coefficient. But also when I apply this algorithm that I had before for solving the problem in the commutative case to the constant coefficient. So this will give me a set of numbers, and all the common divisors of these numbers will be my candidates for k. And please make sure that you know that these are really just candidates, so the real k will be included there, but there could be several more numbers included. For example, if you take p equals L squared, and L looks like this, then what will this set from before be? So the degree of p in s is equal to 4, the degree in x is equal to 4, the degree of the leading coefficient will be 4, and so on and so on, and you will get 4. But the real k is 2, so it's the divisor of this 4 here. And in our example that we had that we started with from before, we get this set of k in this set here, and the common divisor is just 2. So here we get the real k. So now comes a nice trick that I promised you. So first we saw how would we set up a linear how would we set up a system to solve this problem now when we have given this k. So we can let L tilde be Euler polynomial with undetermined coefficients, where the degree is such that we just take the degree of p and divide out k. And then we can make this ansatz here. We take p minus L tilde to the k equals 0. Yeah, this is straightforward. We can do that. But the problem is that we wind up with a nonlinear system. But so if you look closely at this nonlinear system, it's not too bad to solve it. It's quite okay. But this doesn't work if you choose the wrong k, so we have to try out all the candidates for k until we find the correct one. And even this trivial approach does not really help me with solving this problem here. This is when it doesn't help me with that. So this is when the nice trick comes in. So this I discovered when I was actually rehearsing some basic group theory lecture with a friend of mine, and we were computing the centralizer of some subset of a group. And we observed the following, that if you take P times L, then this is equal to L to the K times L, which is equal to L to the K plus 1, which is L times L to the K, which is equal to L times P. So we can set up the following linear system. We take an L tilde with undetermined coefficients, and take P times L tilde minus L tilde times P. So this usually does not commute. But here we use this unlikely commutation that happens here. And in here the undetermined coefficients will pop up linearly. And this can be solved easily. And if we solve this, we get a Q vector space of solutions, which will be typically be two-dimensional and Y two-dimensional. So if we apply it to the example we have given here, then one solution will look like this in the basis. Will look like this, which is nice. It almost looks like the L that we want to have. And the other element in the solution space will be this. And why is this one in here? Yeah, well, that's rather easy to explain, because what commutes with L? Well, L itself and rational numbers. Rational numbers that do not get affected by the commuting with S. It doesn't change anything. So this is why the constant term here is missing. But so we have to combine these two solutions to get the real L, which can be easily read off from the P that we start with. So the advantage of this method is that we get a linear system, and the system is only nonlinear if the solution space is greater than 2, which actually does not happen. I mean, it can happen, but usually when it happens, then it means that you have chosen the wrong candidate K. Because you have chosen K too small. You can choose a little bit bigger. And this procedure always works if the candidate K for K is smaller or equal than K. It will always produce a right solution. Okay, so now I just treated the shift case, but this also works for the differential case. And notice that where did I use that we are working in a shift case? In a shift case, so I only use this when I computed the candidates for K, which is when I looked at the constant coefficient. In the differential case, I can do almost the same, but I just look at the leading coefficient, which will be a power. And for mixed cases, I can always reduce a mixed case to the pure differential or pure shift case by this theorem, which is a classic theorem, which is sometimes called the Hilbert twist reduction. So a very fancy name. But it's an isomorphism between two oral algebras. So I start with one oral algebra which has a non-trivial shift and a non-trivial derivation, and I end up in an oral algebra which has only a non-trivial shift. You have to pay attention a little bit, because if you do that, so the input should be an oral polynomial with polynomial coefficients, but the output will have rational function coefficients. But this is not too big of a problem, because the constant coefficient after you apply the map will be of this form. You have the numerator divided by denominator to some k. So you can actually use both the numerator and denominator to get the candidates for k. So this is not a real problem. And then once you have the candidates, you can switch back to the original P before you apply this Hilbert twist reduction, because then you don't care anymore that you only need a shift or only need a derivation, because that's when you set up the linear system. Okay, as I said, it's just a first step to where I really want to go to, which is solving this problem here, the P of the form A times L equals to K, to the power of K. So what we can do is we can solve it in the commutative case, we can solve this. It's also possible to solve this if I multiply L to the K by some rational number, which is easy because I can always make it monic. I can also kind of solve it here when I multiply L to the K with some polynomial. This is a bit more technically involved and it requires a little bit of heuristics, but it's possible. Where it gets difficult is with these two cases here, when I get sums in there. It's a little bit difficult to distinguish these sums. And what I'm hoping for is with this trick that you, if you have a given p like this, and you multiply with an undetermined, with an OR operator with undetermined coefficients, and you take this difference here, as we did in this case, then it commutes partially. It commutes with this L to the k factor here, but it has a part where it does not commute. And I hope that it's somehow possible to make use of this, that it commutes with some factors, but not all of them. Okay, the conclusion, what did we see? We saw what I mean by right squareiness of OR polynomials. I explained to you how to compute the radical of an OR polynomial by setting up a linear system with unlikely commutativity. And I'm hoping to be able to exploit this partial commutativity in this case here. And if anybody has any ideas or any thoughts about this, I would be happy to discuss this later on. Thank you very much.
Thank you.
Yes?
So on your trick, how to get this, that L commutes with the power of L, basically. So one reference that I can give you here is especially for differential polynomials, there was in the 1920s Bushnell and Chambry. I don't know how to pronounce those names, but there's some ideas that you'll definitely be able to use there.
Okay.
And to our discussion with the derivation on the thing, so if you have, of course, order 1 differential polynomials or shift, then of course this will.
Yeah, but in this case it's rather.
It still stays an interesting problem, and right away email me once you solve it.
Okay.
Okay, thank you very much.
Thank you.